Okay, so we've been talking about gases, and we really talked about a number of gas laws last time. We also talked about units, and again, there's many different units for gases. The three sort of big ones that we come across most in this class: atmospheres, millimeters of mercury, and torr. And remember that a millimeter of mercury and a torr are pretty much a one-to-one relationship. 760 is sort of the conversion factor for everybody else there. 1 atmosphere is 760 millimeters of mercury and 760 torr. We got into the idea of some gas laws. We talked about Boyle's law, which dealt with the pressure volume relationship. And that was at constant temperature. And what we saw there, as pressure goes up, volume goes down, and vice versa there, pressure goes down, volume goes up. Again, smaller volume, a lot more collisions occurring, higher pressure, larger volume, less collisions sort of occurring, lower pressure that occurs. We also saw Charles' law, which dealt with sort of volume and temperature relationships. V1 over T1 is equal to V2 over T2. This is at constant pressure. The important part of this sort of formula, along with pretty much all gas law formulas, is the temperature. It always needs to be in Kelvin. So no matter what situation, it's got to be in Kelvin. And again, as we talked about, even if you're sort of given the temperature in Celsius and you're asked for the answer in Celsius, you do need to turn it into Kelvin to go into the gas law and then kind of do the conversions afterwards. Relationship we sort of saw here was basically volume goes up as the temperature goes up, and volume goes down as the temperature goes down here. And as we talked about last time, that is essentially the way that it's able to maintain the constant pressure. So it's that volume that basically adjusts as the temperature increases or decreases to allow really the same number of collisions and to keep it at constant pressure. The sort of fact that we would know is obviously we increase the temperature, we expect gas molecules to be moving faster. And if we lower the temperature, they would be flying around slower. Kind of on the same vein here with this is Guy Lusik's law. And that is P1 T1 equals P2 T2. And once again here, temperature does need to be in Kelvin. And this is at constant volume. So the difference between the two is also what we talked about, because in this situation we have sort of a rigid volume, it does not move. That means that when we do increase the temperature, we're definitely going to get more collisions going to occur because we're not going to get that volume to adjust in that situation. And what we would see is the pressure would go up as the temperature goes up, and pressure would go down as the temperature goes down. Once again, the opposite being true. As we lower the temperature, it'd be moving around slower, longer for collisions to occur, and we have no, again, adjustment on the temperature there. We had our friend Avogadro and his law, which is a little V1 N1 equals V2 N2 action here. N is the moles. And this is actually at constant temperature and pressure in this situation. And the relationship here is basically the volume and the number of moles are sort of proportional to each other. We also saw that sort of an application of Avogadro's law is in sort of gas stoichiometry. If you are at sort of constant pressure and temperature, much like we could kind of do a mole to mole relationship in a stoichiometry situation, we could do a volume to volume relationship using the coefficients in the balanced equation if they're all gases. Sort of putting all these guys together gives us our ideal gas law, which is our PV equals nRT. And obviously different than the others, there's kind of no two temperatures, no two pressures, sort of a one and done situation. It is also the most restrictive. Again, does need to be atmospheres when you are using this equation. Liters for the volume, moles there for N, and T does need to be in Kelvin. And the reason for all that is the value of the gas constant, which is 0.08206 liters atmosphere Kelvin mole. So that gas constant has all those units, and that's what everybody else needs to be in for everything to properly cancel out when you use this. We also talked about STP, which is standard pressure and temp. And it does represent values. The pressure is 1 atmosphere, or like its equivalent, or the temperature here is a 273 Kelvin. And if you happen to be at STP conditions, there is sort of a conversion you can use sometimes, which is 1 mole of any gas will equal 22.414 liters in that case. A reminder about that conversion, it has to be STP conditions for you to use it. If it's not, you definitely should use the ideal gas law. Also, the good news about that one is you can pretty much use the ideal gas law in any situation, standard or non-standard conditions. So if it's standard conditions, you just put the numbers in and it all works out the same. Any questions on any of those gas laws we cranked through last time, I think? All right, so I think we have one more sort of example here. What is the volume in liters that's occupied by 49.8 grams of HCl at STP, hydrogen being 1.008 and Cl 3545. All right, take a minute or two, see what you come up with. Okay, let's take a look, see how you're doing. So in this case, we're looking for a volume. We have 49.8 grams of HCl. Although it's in grams, we definitely can get to moles. So we definitely have moles there. And we do have STP, which again does represent 1 atmosphere for the pressure. It also represents, again, for the temperature, 273 Kelvin. And as we talked about last time there, they don't usually mention anything about the gas constant. It's just, again, a value that you should know that you should have. So you do have R, the 0.08206. So you can kind of see from all the information sort of given to you, which is sometimes a good idea to do, is sort of pointing towards the ideal gas law, which is PV equals nRT. In this case, we actually just need to do this conversion here to convert it into moles. So we'll take our 49.8 grams of HCl. Using the molar mass from the periodic table, looks like a 3646 situation. 3646 grams per mole. That will get us 40, about 1.37 moles, I guess. Moles there of HCl. And let's see here. Now we got everything we need. We will solve for volume. So volume would be nRT divided by P. Put in our numbers here. We got 1.37 moles. Got our gas constant. And again, as we talked about yesterday, you can use 0.0821, which is a common number a lot of people will use as well. 273 Kelvin, all divided by 1 atmosphere. Atmospheres will cancel, moles will cancel, Kelvin will cancel, going to leave us units of liters when it's all said and done here. And punching those numbers in, 1.37 times 0.08206 times 273, going to give us about a 30.7 liters in that particular case. Any questions on that there? Now, yeah.
Pressure, temperature, does that automatically just go to the 1 atmosphere?
It does will usually say STP. So that's usually, you want to make sure it'll say that in most cases. Yeah.
Okay. You automatically
go that because of the STP. Yeah. Now, because of the STP there, we could have, if we wanted to, right, solve this differently. And because of the STP, we know that 1 mole of any gas will equal 22.414 liters, which means at this point, we could have used this conversion and we could have just went 1.37 moles of HCl, and a mole would be our 22.414 liters, and should get us there as well. So in this case, you did have 2 options as the way you did it. You would not necessarily need to have used the ideal gas law. But as you can see here, you do get obviously the same answer, which means if you don't want to worry about that conversion, or more importantly, worry about using it incorrectly, just use the ideal gas law and put the numbers in and you'll be fine. But you could have kind of shortcutted the calculation and go that way as well. Any questions on the ideal gas law there? Okay. All right, so it looks like we have some room for maybe a few more gas laws here. So taking the ideal gas law and solving for the gas constant, which is R, since these two are basically the same value for sort of two different conditions, we could set these guys equal to each other. And in most cases, though, when you are dealing with gases, unless you open the lid there, usually the moles of gases won't change because they're kind of trapped in a container in most cases. So usually this is constant for both of them. So it does give us one more sort of gas law here, which is sometimes referred to as the combined gas law. And the combined gas law is P1 V1 over T1 equals P2 V2 over T2. This is our normal sort of situation here. Pressures can be any unit as long as they're the same on both sides. Volume can be any unit, once again, as long as they are both the same units on both sides. And like pretty much all gas laws, we still need Kelvin here for our temperature. So this gas law involves a lot of rearranging sometimes. And again, you just remember maybe moving opposites across the equal sign is a quick way to rearrange that. But again, if you have issues with rearranging equations, you should take some moments to figure out, how to properly sort of do that. And again, just kind of the opposite location thing works fairly well with this. So let's take a look at one here. Consider a sample of oxygen gas at 27 degrees Celsius with a volume of 9.55, pressure 2.97. If we change pressure to 825 and heat it to 125, calculate the new volume of the gas, 8.25. So let's take a look. We're going to pull out the information here. So we got a temperature at 27 degrees Celsius that goes with a volume of 9.55 liters. And a pressure of 2.97 atmospheres. We're going to change the pressure there to something 8.25. We're going to heat it up there to 125. And we are looking for the volume in this case. So again, just by pulling out the information, it should pretty much look like the combined gas law is pretty much the right one to use. As we talked about before, it really doesn't matter which ones you label. Most people just kind of label the first stuff number ones and the other guys number two. Again, as long as you keep obviously the information that goes together. In this case, our pressures are both in atmosphere, so we're good to go. We do have to do our normal sort of temperature conversion here. So we're going to add our 273 and we'll end up with 300 Kelvin. Also on this guy here, we'll end up with a 398 Kelvin. In this case, we're going to be solving for V2. So that's a P1 V1 over T1 equals P2 V2 over T2. So in this particular case, we want to keep V2 up on top, and it is. So that's good. That means we need to send our T2 to the top to the other side and pretty much send our P2 to the bottom on the other side, which is basically multiplying by T2 and dividing by P2 to the other side. If you do all that, that will leave you a V2 that equals P1 V1 T2 divided by T1 and P2. So again, you want to make sure that you rearrange that correctly. And even if you do rearrange correctly, you also want to make sure you put the right numbers in the right spots there. I'm going to try that myself. So that's going to go a 297 atmosphere, I think. We got a V1 that's a 9.55 liters. And we actually need T2 up on top, which would be 398 divided by our T1, which is 300, and our P2, which is 825 here. Our atmospheres will cancel, our Kelvin will cancel. Again, leaves us liters up on top, which is what we're looking for, since we're looking for a volume. We got a 2.97 times 9.55 times a 398 divided by a 300 and divided by an 8.25. Going to give us like a 4.56 liters as our answer in this case. Questions on that one there? Now, again, this is probably the one that gives people a fairly difficult sort of situation in terms of rearranging. But it's also quite a useful sort of equation if you don't want to invest the time to remember all the other equations. You pretty much can get all the other equations from this one. So If you want to invest your time, perhaps this is the one to invest with. So if we look at this, which is P1 V1 over T1 equals P2 V2 over T2. If we don't have temperature given to us and we have others given to us, we just scratch out the temperature and there's Boyle's law right there. If we take P1 V1 over T1, P2 V2 over T2, and perhaps we are not given pressures, but we're given volumes and temperatures, you scratch out the pressures and there's Charles' law. If we have our P1 V1 over T1 equals P2 V2 over T2, and we're not given volumes, but we are given pressures, you scratch those guys out, and there's Guy-Lussick's law. If you want to include the P1 V1 N1 T1 version of this equation, and you don't have pressures or temperatures given to you, you scratch them out, and there's Avogadro's law. So, this one is quite useful. You could get all the other gas laws pretty much from it by just scratching out the thing you're not given or the thing that's held constant, and you'll have the other ones, which basically means if you kind of know this one, the combined gas law and the ideal gas law, you pretty much have all the gas laws that you probably need to know. And again, just get rid of anything that is constant. Any questions on that one there? All right. So the next thing we're going to talk about then is density and molar mass. And sometimes we're asked to calculate the density or the molar mass of a gas. And density, as we talked about earlier, though, is a little bit different units for gases than we normally sort of think of a density for solids and liquids. Typical units for gases in terms of the density is grams per liter versus grams per milliliter, grams per cubic centimeter. So density is mass over volume, and you can basically take the pressure times m here. This is the molar mass. And R is our gas constant, T is our temperature in Kelvin, like normal. If you want the molar mass of a substance, molar mass of a substance has units of grams per mole. And you can use this equation here. Molar mass is the density times RT, our gas constant, T temperature in Kelvin, P is our pressure in atmospheres, and the density is in grams per liter. Now, again, you can sort of remember these units if you want. Really, they're both pretty much based off of PV equals nRT. So these are really basically based off of PV equals nRT, and you can use the ideal gas law and maybe like a conversion factor and pretty much get these. So again, you do have a couple of options in terms of how you could solve these problems. And if you can't remember these formulas, you can default back to sort of the ideal gas law and use it to basically figure out both the density and the molar mass of a substance. So let's take a look at one of these, and then we'll talk about how to solve it maybe a different way. So why don't you give it a try here. A 2.1 liter vessel contains 4.65 grams of a gas at 1 atmosphere and 27 degrees. Okay, so let's take a look. So obviously we're looking for the molar mass, which means really you can, plug and chug sort of into that equation. But let's talk about, maybe you can't remember that equation or something like that. You hopefully should still remember the ideal gas law, which is really what that equation is sort of based off of. So if we think about what we're looking for, which are grams per mole, and in this case, we definitely have a volume, which is 2.1 liters. We do have the grams here of 4.65 grams. We have a pressure that is 1 atmosphere. We have a temperature that is 27 degrees Celsius in this particular case. So when we think about the molar mass, we actually have the grams part really given to us. So really the missing thing that we need is the moles part. And we can use the ideal gas law here, PV equals nRT, because we do have a pressure, we do have a volume, we do have a temperature, we always have R. So we can use it actually to get the missing thing that we would need, which would be the moles. And then that we would have basically both things that we need to calculate the molar mass. So that's what we're going to do. We're going to solve for N here. and N would be PV over RT, putting in our values that we do have. They actually are in the right units except for the temperature. So we do have to do that conversion, divided by 0.08206. And here, obviously, we will add our 273 to it. That's going to give us 300, I think there. So put in our 300 Kelvin. Again, everything's going to cancel out here except for the moles. 1 times 2.10 divided by 0.08206 divided by 300 gets us 0.0853 moles. So now we have the moles, we have the grams. So our molar mass in this case is going to be our 4.65 grams divided by our moles. So 4.65 divided by the answer, about 54.5 grams per mole. So again, this shows you can really just use the ideal gas law and just sort of it like a conversion and kind of do a little dimensional analysis to get to everybody to the right units without necessarily having to remember that formula, or you could just remember the formula, whichever way you want to do it. Any questions on that one there? Let's try one more here to finish up, I think. Try this one here. What is the density in grams per liter of oxygen gas at 778 torr and 27.5 degrees Celsius? Let's see what you come up with here. Okay, let's take a look at this one. So once again, if you're looking for obviously the density here, you can use the previous equation to sort of plug and chug into it. So I'm going to show you again how you can kind of use the ideal gas law if you can't remember that equation to sort of get it. So here we are looking for grams per liter. We do have the pressure given to us, which is 778. We do have the temperature given to us, which is 27.5 degrees Celsius. We obviously can use the ideal gas law here, PV equals nRT. And in this case, we just kind of think about what's given to us. We do have the temperature given to us. We do have the pressure. We do always have R. So we really don't have N or V. And if we actually solve for N over V, which means we're going to divide V to the other side, and the RV is going to go this way, RT is going to go that way. We end up with P over RT. N is moles, right, in the ideal gas law, and V is volume, which is liters. That is moles per liter. That is the molarity of this gas. So you could actually solve for N over V, which is the molarity here of this particular gas. And that will give us moles per liter. And why would that be helpful? We're looking for grams per liter, and we want moles per liter is what we will end up with. So it's really a conversion between grams and moles, which means the molar mass can be used, obviously, to do that conversion, which is pretty much what that formula shows us on the previous slide. If we go back and kind of look at it, that is here. That's the PRT version we were just talking about, and basically the molar mass, right, is the guy on top. So again, you could kind of really derive these things from the ideal gas law if you can't remember these equations, which might just be an easier sort of move. So to do that, we got to get everybody in the right units. So we're going to take 778 torr. We're going to convert it into atmospheres by dividing by 760. Gives us an atmosphere. That gets us 1.02 atmospheres. We're going to take our 27.5 degrees Celsius, add a 273, going to give us 300.5 Kelvin. Now we're going to put in our numbers here, 1.02 atmospheres. Our 0.08206, which is our gas constant that we always have, and our temperature in Kelvin, which is 300.5 Kelvin. That is going to give us 1.02 divided by 0.08206 divided by 300.5. That's going to give us 0.04136. The units here, atmospheres cancel, Kelvin cancel. When we do the division, the units become moles per liter, which is our molarity here in this case. Any questions up to that point? As I mentioned, at this point, it really is just a conversion between grams and moles. So we'll use the molar mass. It is O2 and not oxygen by itself, right? So we do need 2 times 16, right, to get the molar mass. gives us 32 grams per mole. So we'll just use that as a conversion factor, 32 grams per mole of O2. Our moles will cancel. So we take that and times it by 32, gets us a density of 1.32 grams per liter. So once again, like I said, you can plug and chug right into the equation, or if not, again, both of those equations are really derived from the ideal gas law. So you could really use the ideal gas law in sort of a conversion type of thing just to get everybody in the right units to kind of do it. So that alleviates maybe having to memorize a couple extra formulas as a good approach. Any questions on that there? Okay, I think this is a good place to lay it up for today.